Thanks so much, Clay. As Clay said, so my name's Deb Ryan, and I'm here with my colleague Stan Kleinsteiber, and we're both based in Denver and work for a company called Sproul, and we both instruct a number of reservoir engineering-based classes for petroskills. So we're going to be TAG. I'm going to present the first half of this presentation today, and then we're going to switch, and Stan's going to jump in and do. For those of you that maybe joined us last year, I did a presentation on black oil PVT in September last year. And today, Stan and I are really going to build on that conversation that we had back in September. So a few of these slides at the beginning, for those of you that joined us in September, you'll see a couple of familiar slides, but we're going to be really diving into a discussion of volatile fluids and gas condensates today and how they really vary from black oil PVT. So with that, I'm going to get started. So why are our fluid properties as reservoir engineers important? So we need to be able to estimate our hydrocarbons in place and calculate reserves, and we need to be able to do that for any type of reservoir, whether it's a gas condensate, a volatile oil, or a black oil. And so understanding what kind of fluid in the reservoir is critically important to those volumetric calculations. We also have to be able to describe the processes that are going on in the subsurface and predict our reservoir behavior. And a lot of that behavior is because of those phase behavior changes that are happening as we're dropping our reservoir pressure. And then once we've gone through and produced our reservoirs under primary depletion, a lot of the time we're also looking at then EOR processes and understanding what kind of fluid is in our reservoir and what kind of fluid we're going to potentially add from an EOR point of view is extremely important. We're not going to talk about EOR today, but we are going to talk about phase behavior in a lot of detail. To calculate, we need to be able to calculate the inflow performance and the rate profiles, production performance, and also as reservoir engineers work with our surface and facilities team to determine what kind of processing requirements and separators and stuff we're going to need on the surface once we're producing our hydrocarbons. How much free gas reduction are we going to get from, if it's an oil, how much gas is going to get liberated? And are we going to have any wax or asphaltene issues? Again, we're not going to necessarily touch on those, the discussion of wax and asphaltene today, but we are going to talk about making sure we're characterizing that phase behavior split again at surface and what that looks like. And then the final thing that's really critical with fluids is really having to identify market and also what kind of price we're going to get for those fluids that we're producing. At the end of the day, we're all trying to make money for our companies, and so identifying product prices because of the quality of the fluid is extremely important. So when we look at some different hydrocarbon mixtures, I'm really going to focus in on a certain piece of this, but we've got 4 different fluids here today that we're showing. A sour gas, which is also a very dry gas. You can see from the composition of this sour gas that really it's predominantly methane, with then some other, doesn't have any other hydrocarbon components, but a lot of other components that would need taking out of that fluid. It's called a sour gas because of that high percentage of H2S that's shown in the composition. And for those of you that maybe aren't familiar with some of this nomenclature, the C1, C2, C3, this is our ethane, methane, ethane, propane, butane, heptane, pentane, heptane, and then the C7 plus being that heptane plus with lumping at the end. So as we move from that dry sour gas to a gas condensate and looking at the difference between that gas condensate and the volatile oil, which is really where we're going to focus today, you can see on that gas condensate there's still a really large percentage of methane in that mixture. The difference, though, between our gas condensate and our dry gas is you can start to see that we're seeing some of those heavier components, the ethanes, propanes, butanes, and those things are really starting to be liquids. And one of the things we're going to talk about today and focus on is how much of that vaporized liquid is going to condense out when we move our fluids, when we drop our pressures and move our fluids to surface, and how we characterize that. You can see for the gas condensate, though, that C7 plus lumping is still reasonably low at 4.99 mol%. When we move across to the volatile oil, we now start to see a fairly big increase in a lot of those mid-ethane through heptane components. And again, a little bit of a jump in the C7 plus portion of this fluid. Compared to that black oil on the last column, interestingly, the methane component in both the volatile oil and the black oil in this particular instance are not too dissimilar. So it's one of the reasons that just the methane component of a fluid on its own isn't enough to characterize it. The big difference that we see in these two fluids is that volatile oil has a lot more of those intermediate ethane through hexane components, and a really big difference with the C7 plus on that black oil, where there's over 42% of that C7, those heavier components in that black oil compared to the volatile. Excuse me. And so this is just an early indication of the fact that C7 plus lumping is a really good indicator of starting to be a good indicator of what kind of fluid we have. So when we're looking at and trying to understand how fluids are going to perform as we drop temperatures and pressures, this particular slide is just looking at a two-component mixture of equal parts ethane on the gas side and N-heptane on the C7 on the liquid side. And is my point? Yes, my point is going to work. So the thing that's really critical with this, before I switch over to the next one to show some of those different fluid types, is understanding that at our critical point on our phase behavior, where we're looking at changing pressure against changing temperature. So this is assuming constant volume. So we're always looking at pressure, volume, temperature relationships for our PVT characterization. If the fluid reservoir pressure and temperature is on the right-hand side of this critical point, it's going to be a gas. It's going to behave like a gas. And if it's on the left-hand side of this critical point, in that single-phase fluid region, it's going to behave like a liquid. What's really important is, depending on what side of our critical point from a pressure and temperature point we sit, is that as we drop down and we drop our pressure, so we drop our reservoir pressure, or we take liquids to surface and drop it down to a separator pressure, is that once we hit either if we're a liquid and we hit our bubble point curve, or if we're a gas and hit our dew point curve, this is the point that we start either as a liquid having those gas bubbles coming out of solution and starting to see two-phase behavior, or as a liquid, this is when we're starting to see those condensed liquids starting to come out of our gas. So it's really important for us to understand where we sit on our phase diagram in order to characterize the fluids correctly. So when we look at our reservoir fluids, dry gas, wet gas, gas condensate, volatile oil, and black oil, these are now all combined on the same phase diagram. So here's our reservoir conditions. This is our original reservoir pressure. Down here, you can read off, this is our original reservoir temperature. And over here on the left, in this light blue dot, is going to be our surface separator conditions. So much lower pressure than our original reservoir conditions, and also much lower temperature than what our reservoir conditions are at. So we need to take those two different pieces into consideration. Last year when we did this webinar, we focused on this black oil window, and you can see the critical point for each of these different fluids is shown by the red dot. What we're really going to focus in today on is that gas condensate and the volatile oil. So what you can see is, for a given reservoir temperature and pressure, in our gas condensate, we're on that right-hand side of our critical point, so at initial reservoir conditions, we're gas. However, as we drop our reservoir pressure and we start depleting the reservoir and producing our hydrocarbons to surface, we're going to eventually hit that dew point pressure line, where we're going to start seeing liquid dropping out in the reservoir. We're going to potentially form a condensate bank, a local condensate bank around our wellbore, as that liquid pressure is dropping in the new wellbore region, and we're dropping that liquid out of the gas in the reservoir. When we bring that gas to surface, we're going to continue to get some of that vaporized liquid dropping out in our separator. And Stan's going to talk a little bit later about the importance and the characterization for that, and the difference between different correlations to understand what that vaporized liquid component is. For our volatile oil, we can see our critical point over here, And our initial reservoir conditions were on the left-hand side. So initially we're liquid and oil in the reservoir. But again, when we now come down and we hit our bubble point, this is where we start to see that gas starting to increase in our reservoir and gas rates increasing at surface as we're liberating that free gas out of the volatile system. And again, understanding how quickly that's going to happen and how much gas is going to be liberated. And one of the things Stan's also going to talk about is how rich that gas is, because again, when we bring that rich gas to surface, we're potentially also going to see some vaporized liquid continuing to drop out of that very, very rich gas that has a lot of those ethane, propane, butane components in it as well. This is really where we're going to focus today in terms of our reservoir characterization of our fluids. So again, looking at these same fluid types, the dry gas and the wet gas, our gas condensate and volatile oil, where we're going to be focusing today, black oils that we talked about in September, and this indeterminate oil, sorry. What's really important with this is that if a initial gas oil ratio, so when we're still above that bubble point, if that gas oil ratio is 1900 or above, we are always a volatile oil. However, if we're in this indeterminate piece between a black oil, which is less than 1500, or a volatile oil of 1900, we have to wait for the lab results to come back to tell us something about what that gas composition is. Is it a rich gas and it's more volatile and it's going to sit in our volatile oil, or is that liberated gas a little bit drier and is going to behave more like a black oil? So this indeterminate region of initial gas oil ratios is really critical that we have lab data in order to understand exactly how these fluids are going to behave in the subsurface and then again at surface in our separators. Interestingly, so gas oil ratio is usually a pretty good indicator. You can see the increase in gas oil ratios where essentially for dry gas it's 100% gas and we have very, very little liquid dropout. Interestingly though, this is a pretty good indicator, gas oil ratio, of what kind of fluid we have. Interestingly though, that API, that stock tank API, the density of the fluid at surface is not a really good indicator. When we're in a black oil, you can see that it could be anything. Black oils can be characterized anything in that sort of almost 10 to 60 API. Gas condensates and volatile liquids are very similar. So not a very good indicator. If that's all we have is a GOR and an API, we're not really going to be relying on that API to tell us if it was a gas condensate or a volatile oil in our reservoir. It's just something to really keep in mind when you're looking at these values and when you have some of this data. The thing that is a really good indicator though, like I showed in those different examples a couple of slides ago, is that mole percent of the C7 plus component does start to tell us something about how many of those heavier components sit in the liquid and where we can classify those liquids. So again, for those wet gases, dry gas has almost no liquid, so that's why this is so low. Wet gas, we're starting to see a little bit coming in, but not very much. This is where you can really start to see some difference between the gas condensate and the volatile oil. And we saw that in that example that I showed. And then really going even higher, and again, we saw that final crude that had over 42% in that example I showed on a C7 plus basis. So really coupling that initial GOR and the C7 mole percent is going to be a better indicator for us than the API. And also, interestingly, color isn't necessarily a good indicator of whether a crude is from a volatile or from a black oil type system. So color isn't a good indicator at all. So that's just something to keep in mind. So this is an example from the Powder River Basin in Wyoming, for those of you that are familiar with this area. And we see what we've got plotted here is that producing gas oil ratio against that C7 mole plus. So those two really good indicators of what kind of fluid that we might have in the subsurface. The green points are all considered to be black oils. You can see they've got much higher. Here's our, my little thing popped up. Here's our C7 plus. So this one's at that 20, going all the way up to a 56 C7 plus. and really low gas-oil ratio, producing gas-oil ratios. Then we come up here with these orange square diamond points being classified as volatile fluids, and then seeing that switch here at 12 mol% to gas condensate. And this black line through here is a condensate correlation that Sam's going to talk about a little bit further on in the slide, that is used to characterize these volatile fluids. And you can see through the gas condensate and the volatile and some of these lighter black oils, this correlation does really well at characterizing the overall behavior of this fluid. But because it is a gas condensate correlation, as we get more into a heavier, more traditional black oil, this correlation isn't very good, which is fine, it makes sense. And so it's also why it's really critical that we understand what kind of fluids we're dealing with when we're choosing the correlation to characterize our fluids and trying to understand the future behavior. So there's a couple of key properties that we need to think about when we're doing our fluid characterization for volatile fluids. Solution gas-oil ratio, so that volume of dissolved gas per unit of oil. This is consistent with it's the same solution GOR that we have in black oil. So how much gas is being liberated from the oil when we drop it below bubble point. The thing that we need to consider with volatile fluids, both for the gases coming out of our gas condensates, but also those vaporized gases that are coming off the volatile fluids, is we have to also consider what this vaporized oil gas ratio yield is, the RV term, compared to the RS. And this is the volume of surface oil dissolved in that unit of volume gas. And it's a reciprocal of that producing GOR, that producing gas-oil ratio RS. But like I said, it's really critical to understand how much liquid is going to be sitting in some of these heavier, wetter gases that's going to drop out, and making sure that we're characterizing that liquid as part of our overall volumes and characterization is excruciatingly critical to getting it right in terms of future production and future production volume. And then our saturation pressures, if it's a liquid, volatile oil, liquid initially, and how much gas is going to evolve when we hit the bubble point, or if it's a gas initially, and we're hitting that dew point, how much liquid is going to vaporize as we continue to drop below that dew point for our gases. This slide is really interesting for our volatile fluids. So what we're looking at here is the percentage of liquid volume. So you can see the green line is our volatile oil. So at initial reservoir pressure, very near critical. So our reservoir pressure and our critical pressure are very, very close to where that dew point, bubble point is on our liquid, and the dew point is on our gas. So here with this green line, we're 100% liquid initially because we're a volatile oil. And on the other side of that, for our gas condensate, you can see we've got 0 liquid and we're 100% gas at reservoir conditions. But because our initial reservoir pressure is very, very close to that saturation pressure, the bubble point for the volatile oil and the dew point for the gas condensate, as soon as we drop this initial reservoir pressure just slightly, what we see is we instantly drop from 100% liquid down to about 55% liquid, where all of that additional liquid volume has now been vaporized as gas, or has expanded as a bubbled off as gas. And the same thing on the gas condensate side. As soon as we've dropped that reservoir pressure just a tad, instantly we're going from 100% gas and no liquid to 45% liquid that's being vaporized out of that system. So we see very quick changes, and then once we continue to drop this pressure, we're continuing to see additional liquid dropping out, both of our oil and our gas condensate, as more and more of that volatile fluid is vaporizing into gas. This is one of the reasons that understanding whether we're an oil or a gas initially and how close we are to the saturation pressures is really critical to understanding what the future behavior and the performance of our liquids is going to look like in production time, and also at our separators at surface. So from a fluid flow point of view for our volatile oils, So in that early slide, I talked about the fact that that initial gas-oil ratio is going to be somewhere in the vicinity of 1900 to 32 standard cubic feet of gas per stock tank barrel of oil. We're single-phase liquid until we hit that bubble point. And then, like I just showed in the last picture, we have a rapid decline in oil flow as we drop below that bubble point pressure, because we're starting to see a lot of that that gas coming out, and a lot of that gas still has some of that vaporized condensate in it. It tends to be a much heavier, wetter gas. On the gas condensate side, we're seeing those initial gas-oil ratios being more in the 3,200 to 15,000 standard cubic feet per stock tank barrel. Above that dew point, we're single-phase gas. And then once we hit that dew point, we're seeing primarily gas with that vaporized condensate component in it, and that condensed liquid that's dropping out often drops out in the reservoir and forms a condensate bank around the wellbore. So this is condensate liquid in the unstimulated wellbore region around that drops out. So I think with that one I am switching, yes. So I'm just going to quickly stop sharing my screen.
Thank you, Deb. I'm going to, let's see, I'm going to change the presenter over to Stan, so that should pop up for you, Stan, and then you should be able to take over here. You're on mute.
All right, is that better?
Yep. Yep.
Good. All right, good morning, everyone. Or good afternoon, wherever you are in the world. All right.
And if you'll just hit share, then
okay, yeah,
see
help.
PowerPoint here.
Hang on. Oh, there it is. Share my desktop, monitor 1.
All right.
All right, that's better. Thank you, Clay.
Yep, looks good. Thanks.
All right. All right, so as Deb said, let me talk for a few minutes here about gas condensates, how they're different than wet gases, and then volatile oils, how they are different from the black oil fluids. The first thing I'd like you to remember is that the properties of a gas condensate, the PVT properties that we use in subsurface calculations, the properties of that gas condensate fluid in the subsurface are not the properties of your separator gas. Because as that condensate leaves the perforations, it has all of this liquid vaporized in it. So we have to recombine the surface separator gas and stock tank condensate to be able to calculate the appropriate properties. In our deliverability and well test analysis calculations, the flow rate of gas leaving the perforations expressed at standard conditions is not the same as the surface separator gas rate, because once that liquid, or once the fluid reaches the surface, condensate drops out and shows up as stock tank liquids. So we have to recombine or take that condensate to its vapor equivalent so that we can use the proper reservoir gas rates to calculate permeability from our transient tests to predict well productivity. And the same concepts hold for material balance. We have to look at the cumulative production of everything that comes out of the ground, the separator gas and the vapor equivalent of the condensate that shows up at the surface. This is an example of that difference. Here's a slide that I made where I'm producing a 0.7 gravity separator gas and 50 degrees API condensate. And here, when the gas-oil ratios are very high, 100,000 standard cubic feet per barrel, which is equivalent to a condensate yield of 10 barrels of condensate per million standard cubic feet of separator gas. The gravity of the reservoir gas in the subsurface is very close to 0.7. The rate of gas leaving the perforations at standard conditions is very close to the surface separator gas rates. But as that GOR declines, as the liquid yield increases, once we're here at the 15,000 cubic feet per barrel range, where our rules of thumb say now we're definitely dealing with condensate fluids. Now, even though it's still 0.7 gravity gas at the surface, it's 0.9 specific gravity gas in the subsurface. And the reservoir rates leaving the perforations, expressed at standard conditions, are about 5% greater than the surface separator gas rates because of the condensed liquid. As the gas-oil ratio gets lower and lower, as we get closer and closer to volatile oil behavior, these very rich gas condensates can have gas gravities in the subsurface of greater than 1 and can have reservoir gas rates that are 10 to 20% higher than the surface separator gas rates that we measure. One other point that I should make, we use this 15,000 cubic feet per barrel, 4 mole percent C7s plus. It's kind of that bright line between wet gases and condensates. At gas-oil ratios of 15,000 cubic feet per barrel to 50,000 cubic feet per barrel, depending on the reservoir temperature, there probably is some condensate dropout in the rock once we go below dew point pressure. But that condensate dropout is not enough to really impact my engineering calculations for the overall recovery factors, even though there is some condensate dropout. But once we get greater than 4 mole percent C7s plus in the subsurface, once our gas-oil ratios are greater than 15,000 standard cubic feet per stock tank barrel at discovery conditions, you are definitely dealing with a condensate. As you decrease your reservoir pressure, you are going to have liquids drop out in the reservoir, and we have got to have good PVT characterization so that you can understand those impacts on well deliverability and on overall recovery of the surface products that we're trying to sell. So, as long as the reservoir pressure is above the dew point, my life is good. Everybody is single phase. But of course, once the producing pressure drops below dew point, we start to condense liquid around the perforations. That liquid dropout around the perforations is called condensate banking. It acts as a skin factor on the well, and depending on the shape of the gas-oil relative permeability curves and the flow velocities, it can really impact well deliverability. As an aside, you see exactly the same thing in a volatile oil once we go below bubble point at the wellbore. Because gas boils out of the oil, that gas inhibits the effective permeability of the oil, shows up as a skin factor in the near wellbore area. As the reservoir pressure at the drainage boundary falls below dew point, now liquid is condensed everywhere in the pore space, and so we'll lose well deliverability because now we're losing effective permeability to gas everywhere in the interwell area. And in material balance calculations, now the properties of the gas still in the reservoir are no longer my initial gas properties. I have to account for this condensed liquid by using the two-phase Z factor. In the September webinar that Deb talked about black oils, there are a lot of correlations that are available for you to predict black oil performance. For gas condensates, some of the ones that I have seen is one of the earliest ones that I found was written in an old magazine called Petroleum Engineer International back in the late 1970s. And Garb gave me a correlation to be able to predict what the vaporized gas condensate ratio would look like at pressures below the dew point. Cho, in this SPE paper, presents a correlation showing the maximum condensate dropout as a function of the mole percent C7s plus and the reservoir temperature. As Deb showed you in the phase envelopes, the hotter and hotter your reservoir temperature is, the further and further away you're going to get from the critical temperature of the gas, holding the composition equal, and the less condensate dropout you're going to have because you're getting closer and closer to that dew point boundary of the phase envelope. Probably the most useful set of correlations that I've found were published in this SPE paper 112977 by Oval and his co-authors. He presents a relatively easy to use correlation for predicting the dew point pressure. And that dew point pressure is good to plus or minus about 20% of what the dew point pressures we can measure in the laboratory. He presents a correlation for predicting the producing gas oil ratio or the vaporized condensate ratio at pressures below the dew point. He presents an alternative correlation for calculating the gas gravity of the gas that's still in the gas phase at pressures below the dew point. And, like in the previous slide, if you want to make some assumptions as to what your separator gas gravity is and your stock tank condensate gravity, I can recalculate a gas oil ratio based on the reservoir gas gravity and the surface products. So you can use this correlation or this correlation to calculate condensate yield as we get further and further away from the dew point. And then, as Deb showed you in the slide from the Powder River Basin, they presented a correlation for predicting gas oil ratio if you knew mole fraction C7s plus, or predicting mole fraction C7s plus if you observe the gas oil ratio. And looking at that laboratory data from the Powder River Basin, that's a pretty nice correlation for these bright lines of less than 4 mole percent, I'm going to treat it as a wet gas. Between 4 mole percent and 13 mole percent C7s plus, gas oil ratios of 15,000 to 3,200 cubic feet per barrel, we're going to see dew point gases in the lab. Greater than 13 mole percent C7s plus, gas oil ratios of less than 3,200 cubic feet per barrel, I'm going to see volatile oil behavior. These correlations talked about the dew points, good, plus or minus 20% of the measured laboratory dew point pressure. These condensate yields, when I look at those yields predicted from the correlation compared to laboratory data, they're only moderately useful. They're not terribly accurate. So for good reservoir management purposes, it is essential in these near critical fluids that we get PVT samples, we send them to the labs and have the appropriate tests run on them. So in volatile fluids, it's sometimes difficult to obtain representative PVT samples. If you produce at too high a drawdown, you run the risk of going below the saturation pressure. And so I'm either going to have gas breakout near the well in a volatile oil or condensate dropout near the well in a gas condensate. Now, if you choke the well back and you're trying to take surface samples, if you choke the well back, you're decreasing the drawdown. If you keep the drawdown too low, you may not be able to lift all the liquids out of the tubulars, so you're producing below the critical rate, and you're not going to get a stable gas oil ratio at the surface. All of this tends to require or cause the fact that we'll miss some of the heavy ends, which really govern the bubble point pressure of the oil, the dew point pressure of the gas. Taking wireline conveyed MDT samples, modular dynamic tool samples, are accurate if you promise me that the pressure coming into the sample chamber is above the fluid saturation pressure. If you don't have enough well productivity to generate enough drawdown to get fluids into the samples when above the saturation pressure, you're probably better just bringing everything to the surface and taking surface recombination samples. Because there are studies in the literature that show that in around an unstimulated vertical well, even if you're producing into the well at a pressure below saturation pressure, right around the well, you can build up a high enough saturation of whatever the phase is. Liquid dropout in the gas condensate, gas breakout in a volatile oil, that when you bring those fluids to the surface, as long as you're producing above the critical rate, Every molecule that gets into the perforations, makes its way to the surface, shows up in either the surface separator or the separator gas or the separator liquid. Take companion samples and you recombine them. And that is around an unstimulated well. Those of you that work in assets where the permeability is so low that you have to hydraulically fracture the well before it'll flow, our ability to get good PVT samples is really hard, because now you got that whole big fracture that you're plating these fluids out on, condensing liquids out of a gas condensate, and it's very difficult to build these critical flowing saturations. So very challenging to get good PVT samples in critical fluids, especially if you can't produce the fluid at a substantial rate above the saturation pressure into the wellbore. Once you've gotten your samples, whether they're obtained by surface recombination or by wireline conveyed MDT, we're going to get a well stream composition. If I've got separator samples, I'm going to get a separator sample or an analysis of the separator gas, an analysis of the separator liquid. In the separator liquid, I want to make sure that I get an extended analysis to the C30s plus, because if I'm going to do any phase behavior modeling, the properties of those heaviest components affect the saturation pressures. If I'm simply taking downhole MDT samples, I still want an extended heavy end description so that I can do a good job of predicting the saturation pressures. We're going to run what's called a constant composition expansion test. Some people know it as the flash test, for determining the saturation pressure, bubble point oils, dew point gases, and the pressure volume relationship below the saturation pressure. Though I don't use this in reservoir engineering calculations, all I will use is from the saturation pressure above to initial reservoir pressure. We're going to take some of those fluids at the saturation pressure and run separator recovery tests to make sure that we understand how that reservoir fluid splits into the surface products that we're going to sell. The primary difference between volatile oils and gas condensate fluids in the PVT testing description is how do we predict, or how do we study in the lab what happens below the saturation pressure. Those of you that are used to working in black oils know that we order what is called a differential liberation test. In volatile oils, we don't run differential liberation. In gas condensates, we don't run differential liberation. We run what's called a constant volume depletion test, and I'm going to talk about that in the next slide. For all of these tests, we need to make sure that we do a very good job, not only of getting good PVT samples, but of recording the appropriate reservoir temperature that we want the laboratory to run our experiments at. And I can do separator recovery tests and constant volume depletion tests on the computer with an equation of state program, as long as I have some experimental data to tune the equation of state to. So we're always going to want to run at least a constant composition expansion test in the laboratory so that I have some data to tune the EOS to. Now, what is the difference between a constant volume depletion test and a differential liberation test? In a differential liberation test, you took an oil at its bubble point, you dropped the pressure, you opened the valve and took off all the gas. You close the valve, you drop the pressure, a little more gas boils out, you open the valve, you take off all the gas. In a constant volume depletion, whether it's a gas condensate or a volatile oil, we're going to start at the saturation pressure. I'm going to drop the pressure. I'm going to enter the two-phase region, and in this slide, some liquid condenses out of this gas. I'm going to open the cell, and I'm going to take some gas out, but I'm only going to take the volume of gas out that I need to return the cell to the volume that it had at the start of the experiment. I'm going to take that gas and I'm going to measure its composition. And then I'm going to either measure or calculate the surface products that will be produced from that reservoir gas. I'm going to open the cell, increase the cell's volume a little to drop the pressure some more. Notice more liquid condenses. I'm going to open the cell again, take off now a different gas, and only the volume of gas needed to return the cell to its original volume. Take that gas, measure its composition, calculate or measure the surface products that come out of it, and then do that in a repeated number of steps until I finally get to a low pressure. In constant volume depletion experiments, we never take any liquid out of the cell. It's only the gas with the vaporized liquid in it, and that is the same for whether it's a volatile oil or a dew point gas. Now, what about volatile oil fluids? The big differences in a volatile oil is the solution gas that is liberated has a lot more C7s plus vaporized in it than from a black oil. This happens to be two samples from that Powder River Basin slide that Deb showed before. Here's a black oil with a bubble point pressure of 2,680 psi, a solution GOR of 822 cubic feet per barrel, a BSABO at the bubble point pressure of 1.5. In the differential liberation test, they dropped the pressure to 2,415 psi. They opened the cell and they took out some gas. That gas had vaporized in it 1.6 mole percent C7s plus. So, from that oval correlation, I would think this is going to have a liquid yield of around 25 barrels per million. And because this gas boils out slowly from the oil's effective permeability stays high. And so the liquid rates that I'm showing at my stock tanks have mostly reservoir oil and a little bit of vaporized condensate. This volatile oil sample had a GOR of 2,640 cubic feet per barrel, had an oil formation volume factor of 2.75 barrels per barrel at the bubble point. From the constant volume depletion, the first step they took decreased the pressure to 3,915 psi. That gas had vaporized in it 7.3 mole percent C7s plus. So from the Eval correlation, I would predict a liquid yield for this gas of over 150 barrels of condensate per million standard cubic feet. And like Deb showed in that slide, when you go below the bubble point in a volatile oil, you might, within a few hundred psi, go from 100% liquid in the rock to 50% liquid, 50% gas. And if you look at a gas displacing oil relative permeability curve, by the time you've got a gas saturation of 50%, you essentially have no effective permeability to oil. So now, the liquid that you're producing at the stock tank is almost 100% the vaporized condensate that comes with the evolved gas, very little liquid flow. So in our material balance calculations, in our volumetric calculations, in our reservoir simulation, in black oil models, we assume that liquid in the rock shows up as liquid in the stock tank and evolved solution gas. Gas in the rock shows up as gas in the separator. But in volatile oils and condensates, the gas in the ground not only is separator gas, but I get this vaporized liquid that condenses to liquid at the surface. And if you do not account for this vaporized liquid in a volatile oil study, you will substantially underestimate the amount of liquid that you will recover. This is a paper written by one of John Lee's graduate students at the University of Houston. He was studying the behavior of the unconventional, massively hydraulic fractured horizontal wells in volatile fluids, but it really doesn't matter. The phase behavior would be the same in a vertical well with moderate permeability as opposed to a massively fractured horizontal well in low permeability. He gave an example with several different fluids. This is just one of them. Remember, Deb said that volatile oils, the reservoir temperature is less than the critical temperature of the fluid. Here I've got 22 mole percent C7s plus, 2561 cubic feet per barrel GOR, a very high API gravity. Remember, Deb said API gravity is a lousy determinant of fluid type. And they built some simulation models using a compositional formulation. So instead of PVT tables, we have an equation of state to predict performance. And we get, after 10, 11,000 days, we get about 9 million barrels of recovery. Well, instead of that, instead of using experimental data, if I used the standings correlation for black oils, because the black oil correlations don't do anything for vaporized condensate, I'd have predicted less than a third of the true recovery. Even a more modern black oil correlation like Vasquez and Beggs, I'd have been under 50% of this, because the black oil correlations do not teach you anything about the amount of vaporized condensate that's still in the solution gas below the bubble point. So in summary, gas condensates typically have initial gas-oil ratios of between 3,200 and 15,000 cubic feet per barrel. There is significant liquid dropout in the reservoir when the pressure falls below the dew point. And since that liquid has low mobility, for classical engineering purposes, we assume that once it drops out in the rock, you're never going to move. And so you have to understand the liquid dropout to actively or accurately predict the amount of separator gas recovery, stock tank liquid recovery. Volatile oils typically have initial gas-oil ratios between 1,900 to 3,200 cubic feet per barrel. Once you go below the bubble point, massive amounts of gas boil out of the liquid. Because the gas inhibits the effective permeability of oil, free liquid flow in the reservoir essentially stops due to the high free gas saturations. We still make liquid at the surface because the evolved solution gas still contains significant amounts of vaporized condensate. Good PVT characterization is essential to developing an essential reservoir management plan. And to get good PVT characterization, proper well conditioning and sampling procedures are key to getting good test results. And remember, in volatile fluids, gas condensates and volatile oils, we study the behavior of the fluid below saturation pressure by running constant volume depletion tests, not differential liberation. PVT correlations have limited utility in volatile oil systems, so recovery predictions should be based on experimental data. And because of the liquid flow behavior, volatile oils below the bubble point pressure should be studied as if they were gas condensate fluids as opposed to black oils. Last slide before questions. If you want any more detail on the PVT properties of near critical fluids, here are the following classes that Petroskills offers. You can take the class called Reservoir Fluid Properties, Preparation for Reservoir Engineering and Simulation Studies, which is available in a face-to-face format once we can start traveling again. In our gas reservoir management class, we talk about gas condensate fluids and the performance predictions of them in some detail. That's available not only in face-to-face format, but in instructor-led virtual format. Our 10-day applied reservoir engineering class, which is available still in a face-to-face format, talks about volatile oils and gas condensates both. And applied reservoir engineering is also available in our online blended version. and you can take the PVT property modules separately from having to sign up to take the entire Applied Reservoir Engineering class in the online blended format. All right, that concludes my part of this. I thank you for your time, and I'll be happy to answer any questions that I might be able to.
All right, thanks, Stan, and thanks, Deb. That was a really good presentation. I do have some questions that came in during the presentation here, so we can work through those. And while we're doing that, if others have questions, feel free to go ahead and put them in the chat there, and I will add those to the list. All right, so the first question, Deb, this came in on the Powder River Basin slide, and the question asks, I wanted to know what amounts of formation water can be expected typically for the reservoir types we are seeing.
I'm actually, Stan, you looked at those PVT samples in a little bit more detail. Do you know the answer to that one? I'm sorry to defer that.
I don't. For the formations that were studied in that Powder River Basin study, the initial mobile water saturations were not very high. And just to add on to that, the Curtis Whitson, who's a guy that writes a lot about PVT characterization, when he talks about trying to get good PVT samples in the unconventional assets, one of his comments was, because of this liquid dropout or gas breakout, you might really try to take your PVT samples while you're still flowing back frac fluid. But in terms of the Powder River Basin examples per se, I'm not 100% sure about the produced water cuts, but I don't think they were terribly high.
All right. Then let's see. The next question references slide 10. That was the classification of reservoir fluid types from production characteristics. And it asks, is the C7 mole percentage for complete recombined reservoir fluid?
Yeah, those are reservoir fluid properties in that table. So, yes.
All right, thanks for clarifying that. Then the next question is for Stanley on slide 22. It asks, how can we validate the accuracy and reliability of CVD experiment data?
There are some good papers in literature, and then the numbers are not on the top of my head, but part of it is you know the initial composition. So you know how many moles are in the cell. You know the compositions and volumes that are coming out of all the cells. We can do mole by mole sort of material balance tracking. We can look at some of the equilibrium ratios, and there's Hoffman plots, some other things, but there are some papers in the literature on quality control of CVD experiments, and the question points to something that you will find CVD tests that, for whatever reason, were not poorly run in the lab. But I would have to probably dig a little deeper into my files to come up with the actual reference. But if you go into OnePetro and Google quality control for CVD tests, you will find some papers in the literature that address that. I've seen a guy from OMV, Klaus Putsch, had a nice paper about that, and then there were earlier papers. But sorry, that's not a very good answer to your question, but you're right. You do need to do some sleuthing to make sure that the CVD test is accurate before you just take the numbers and run down the road and start making performance predictions.
All right, and then the last question I've got here, unless anybody else enters those into the chat, is in volatile oil in reservoir, once the pressure is below dew point, is it desirable to limit the production from the well?
So first off, if it's in a volatile oil, so now we're going to have bubble points, gas is going to break out. And so really in a volatile oil system, good reservoir management says do whatever you can to keep the fluid above the bubble point pressure. So start putting water back in the ground. Start putting your produced gas back in the ground. Start looking at some way of enhanced gas flooding so that we push the oil out while trying to maintain the pressure as high as we can. In a gas condensate, now the only way you can avoid liquid dropout in a condensate is to never let the reservoir pressure go below dew point. Well, of course, that's very difficult because you're trying to maximize gas recovery, which requires pressure depletion. So then in gas condensates, probably your best bet is to try to understand the magnitude or the impact of the liquid dropout on well productivity, which interestingly enough is more a function of relative permeability than it is of fluid richness. And there are ways that we can mitigate condensate banking. We can never eliminate it. And like in volatile oils, if the liquid content is high enough, we should study the ability to do gas cycling or pressure maintenance operations in the condensate for the purpose of maximizing liquid recovery. So the short answer to the question is, I don't know that it's really helpful to choke the well's production rate as opposed to developing reservoir management plans to try to maintain pressures in black oil, in volatile oils, to try to do something to mitigate condensate banking in gas condensates and evaluate whether the condensate has enough liquid in it for pressure maintenance.
All right. Thank you. And then a couple more did come in. The next one says, will using CVD results not underpredict the liquid production in gas condensates because it assumes that all liquids that drop out remain in the reservoir?
In my experience, no. So I talk about how you can build a mobile liquid saturation around an unstimulated wellbore, but we're talking about only a few inches to feet around the wellbore. Once we get out well away from the well, when you look at the liquid saturations, you look at the liquid viscosities, you look at the mobility of that liquid compared to the mobility of the vaporized or the gas with condensate vaporized in it, those liquids don't move. Or if they move, they crawl towards the well while the gas is running ahead. And so at least in my experience, the CVD test is a reliable way of estimating liquid recoveries in the condensate because, except right around the well, the liquid mobilities are just not very high. And then again, in the volatile oil side, once you build a 40% gas saturation, that gas lives in the big pore throats. The effective permeability to oil is going to be essentially zero. So once we build up enough gas saturation, the liquid mobilities are awfully small, and I don't believe would contribute significantly to recovery below the saturation pressure.
All right. Another question here says, which equation of state do you recommend for a gas condensate reservoir?
Oh, that's a very good question. Coming from Amoco Production Company back in the old days, we used to use a Redlich-Kwong. I think Peng Robinson is probably just as good. I am not an EOS expert by any means, but I think either Peng Robinson or Redlich-Kwong probably do well. The biggest thing is to get experimental data so that we can tune the equation of state to match experimental data before we begin to do predictions.
All right. Next question here says, can you, let's see, I'll paraphrase here. Can you elaborate on any key factors for separator design when we are dealing with volatile and gas condensate fluids? It's too bad we need a facilities person here to talk. One of the things that I have seen
is the more volatile the fluid, if we decant it. So we use multi-stage separation rather than a primary separator and stock tank. You'll tend to preserve the hydrocarbons in a liquid form, which typically are more valuable than hydrocarbons in the gas form. But the actual pressures, temperatures, number of stages, that's why we'd like to run in the laboratory or on a computer with the tuned equation of state several different combinations so that you could maximize the value. And of course, some of that too depends on your transportation options. How are you going to get your gas and oil from the field to the refineries and to the pipelines? What are prices that people are willing to pay? But at least the short answer would be, in volatile fluid, sometimes more stages is helpful than just one primary separator and a stock tank.
Well, I was going to just build on what Stan said a little bit there. It links back to one of the earlier questions as well, and it's really understanding with the project team and the company what's the value driver of the particular reservoir you're producing, and optimizing that for separators, optimizing that in terms of how you manage the reservoir is key in terms of what is maximum essentially for your particular field development, reservoir management plan. So, yeah.
All right, thank you. A couple more here. The floodgates opened a bit. And so I'm sure I'm going to mispronounce something here, but this asks, would you please remark on the reliability of the Oval vaporized oil ratio correlation? And are there fluid properties and reservoir setting ranges where it is more or less reliable?
Oh, that's a really good question. My short answer is I haven't studied it enough over a wide enough range to say where it's good, where it's bad. And I don't have the slides immediately available, but in our gas reservoir management class, I've got a slide where I have these Oval condensate yields predicted from first as condensate yield correlation, or then back calculated based on the reservoir gas gravity compared to laboratory CVD experiments, just one set. And they just, they're okay. The Oval correlation for the one set that I studied, right below the dew point, had much less condensate predicted by correlation than we measured experimentally. And of course, to the previous question, well, how do you know that the experiments were right? Fair enough, I didn't do a lot of vetting of that experimental data. So I don't have a good answer to the question, except to say that the Oval looked better than the GARB correlation from 1978. The Oval correlation is better than you just making a guess. I actually like the yield calculated from the well stream gas gravity as opposed to his yield equation, but we use those with a big rule of thumb. It's like it's in the order of magnitude, but it's not precise to even plus or minus 10%, and you really need some experimental data with that. Sorry, that's not a very good answer, but it's the best answer I've got right now.
No, that's good. All right, a couple more here, and then we can wrap up. So this one asks, what are the odds of CVD data availability for a sample taken from a discovery in the 1980s? And would there still be value in doing a CVD test now if the field has never been produced?
Oh, if the field's never been produced, most assuredly. Would there have been CVD data available? Sure. I worked in gas condensates in the early 1980s, and laboratories knew how to run CVD experiments. Did the engineer that was doing the PVT work order a CVD test? Don't know. But if they've given you some constant composition data, then somebody, a service company, a consultancy could build an equation of state and do the predictions. If your field has never been produced, then by all means, bring some fluids to the surface. It's still in its original state. bring some fluids to the surface and take your samples and run your tests. Now, if you don't have CVD data from discovery and you've been producing since the 1980s, there's probably no reason to go take samples now unless you're planning on doing some sort of trying to change the recovery mechanism, the reservoir management plan, because you'll never reconstruct what the original fluid was. But if the field's never been produced, then yes, by all means, you should be able to get fresh fluid samples and do all the tests you want.
All right, and then lastly, it asks, do you see an increase in CO2 injection for pressure maintenance in retrograde condensate reservoirs?
That's a good question, and you can find stuff in the literature. I know I've got some friends with OMV in Austria that have written about CO2 as a means of pressure maintenance. And yeah, the only thing you have to think about in CO2, just like injecting nitrogen for gas condensate, is what does that do to the phase behavior? I don't know exactly what CO2 would do. Nitrogen tended to elevate a dew point. And so we initially started with nitrogen hydrocarbon buffers in the one field I worked in. CO2 could be done. You're just going to have to make sure you understand that the CO2 in the water are going to cause corrosion. And so you're going to have to make sure your wellbore tubulars are set for the corrosion. You're going to have to take that CO2 out of your gas, because first off, you're sequestering the CO2, and second, nobody wants to buy CO2-rich gas, so you're going to have to take that CO2 out. And like any gas injection project, good geologic characterization to understand sweep efficiency is critical. Because even if the phase behavior effects are favorable, if you've got lousy reservoir heterogeneity and poor sweep, you're not going to have a very good economic project. But there's no reason that you can't inject CO2 as a means of pressure maintenance in a gas reservoir, just like we do CO2 in oil reservoirs for enhanced oil recovery. You just have to understand that there will be phase behavior impacts, there will be production impacts, and there will most certainly be surface processing impacts as well.
All right. Well, thank you everybody for the excellent questions. Stan and Deb, thank you guys so much for your presentation and for the discussion. As I mentioned, we have been recording this, so we'll send that out to you guys along with the presentation materials. I had a few questions about that, so you'll get all of this afterwards, don't worry. Yeah, thank you for spending some time with us today. We hope to see you in future webinars. So thanks again, everybody. Take care and stay safe.
Thank you.
Thanks, Clay. Thanks, Dan.
All right. Thanks, Deb. Thanks, Dan. You guys are good.